All right, hey, in our final section here in Chapter 2, we're going to look at the real deal, the precise definition of limits. So that's Section 2.7. We're going to look at the real deal, precise definition of limits. So in Section 2.2, when we started our journey here in limits, we actually looked at an informal definition of a limit. And here's what we said at that time. So our informal definition of a limit that we provided in section 2.2 said that the limit as x approaches a of f of x equals L means that when x is close to a from both sides of a but not equal to a, then f of x is close to L. Now here's the problem with that definition. This is a problem in the math world. The problem with this informal definition is, what does close mean? And how close is close enough? And see, that doesn't cut it for a mathematician. We have to be able to quantify what close means and how close is close enough. So I'm going to break it down into two cases here, or two parts. Part one, the informal definition that says, quote, when x is close to a. Okay, mathematically, when x is close to a, that means we want to be within delta units of a. That's the Greek letter delta. Now I'm going to use this graph over here to the right to help make sense out of this. So first thing over here on the right, let me kind of point this out. There's my a. So when x is close to a, that means we want to be within delta units of a. So, delta is going to be some positive number. So let's see, over here is a plus delta. That's the endpoint over here. And over here is a minus delta. So x close to a within delta units of a, that means I can pick any x in this interval. I just have to have x trapped between a minus delta and a plus delta. Well, if x is trapped between a minus delta and a plus delta, that sounds like a compound inequality to me. X is trapped between a minus delta and a plus delta. All right, folks, that compound inequality, I can subtract a from each piece of the inequality to get negative delta is less than x minus a is less than delta. And then I'm just thinking back to something you would have seen in an algebra class. I don't know, maybe like an elementary or beginning algebra class, Algebra 1, a long time ago. A compound inequality like that negative delta is less than x minus a is less than delta, that comes from an absolute value inequality. In fact, the absolute value inequality would be absolute value of x minus a is less than delta. So let me write that down. And I put that in a box, so it must be important. And I just added on one little piece to that absolute value inequality. I started it off with a 0 as less than. And the only reason I did that was, delta, it's just guaranteeing to the casual observer that delta is like a distance. It's going to be a positive number. The second thing we're going to analyze was that very loose language in the informal definition, quote, f of x is close to L. Well, for f of x to be close to L, that means we want to be within epsilon units of L. That's the Greek letter epsilon there. So let's look at the graph to see what that means. It looks like right here, that's L, that's our limit. So, a, as x approaches a, it looks like the limit is L. So we want f of x to be within epsilon units of L. Well, if I'm within epsilon units of L, that means an upper bound would be L plus epsilon, and a lower bound would be L minus epsilon. So we want f of x, we want functional values to be within this region here, we want all f of x's to be trapped between L plus epsilon and L minus epsilon. So sounds like another compound inequality to me. It sounds like f of x is trapped between L minus epsilon and L plus epsilon. Well, just like I did in number 1, I can come to this compound inequality and subtract L from each piece to get negative epsilon less than f of x minus L less than epsilon. And just like I said in number 1, that reminds me of an absolute value inequality. It's the absolute value of f of x minus L is less than epsilon. So let me write that down, and notice I put it in a red box, so it must be pretty important. So that really loose language in our informal definition, x is close to a, and the other loose language, f of x is close to L. When I just said, what does close mean and how close is close enough? What you see in the red boxes here, that tightens things up. It tells us what it means to be close, and it tells us how close is close enough. In fact, I can take what's in the red boxes here, part 1 and part 2, and I can put those together and write the official, real deal, formal definition of a limit. And here is the real deal, formal definition of a limit. F is a function that's defined on an open interval containing a, and then parenthetically, I'm just reminding you that the function does not have to be defined at a. And let L be a real number. Then the limit as x approaches a of f of x equals L, that really means that for each and every epsilon that is greater than 0, and we're talking very small numbers here, there would exist a delta greater than 0, such that when 0 is less than absolute value of x minus a is less than delta, that implies the absolute value of f of x minus L is less than epsilon. So that's using 1 and 2, putting them together. So it's basically saying, in not so many words, what this is saying is, hey, for every epsilon greater than 0, you find an interval that's based on what delta is around a, so it's like on the domain, on the x-axis. You find a small interval around a that for every x you pick in that small interval around a, for every one of those x's, the functional values, the f of x's, if you will, are within epsilon units of L. I always thought, and I like to think, this is somewhat like a game. And I like games. The game is someone gives you an epsilon. So they're giving you an epsilon, which means they want to be within epsilon units of the limit L. So maybe they give you an epsilon value of 0.001. Then the game is, your goal is to find the delta where they can pick any x that's within delta units of a, and all the functional values will be within that epsilon units of L. So now, folks, before we actually do an official proof, and we're going to do an official proof, let's look at an example that kind of highlights what this game is. You're going to be given a value for epsilon, and then we're going to determine the appropriate delta. And here's the example. There's some function f that satisfies the limit as x approaches 2 of f of x equals 6. Don't know what the function is, don't care. We're going to determine delta greater than 0, and it's going to be the largest delta that satisfies in part A, if 0 is less than absolute value of x minus 2 is less than delta, then absolute value of f of x minus 6 is less than 2. So notice in this example, as I keep talking about this as a game, this value of 2, that's an epsilon that someone has given you. Part B, I'm changing the epsilon to be a 1. So write this down, folks, and give yourself some room in your notes when you write this down. Because when I get to the chalkboard, the first thing I'm going to have on the chalkboard is a graph for this function. I didn't want to put it on the slide because it just wasn't enough room. So I'm going to put the graph of this function. Don't know what the function is, don't care. I'm going to put it on my chalkboard, and it's actually going to be a pretty accurate, neat graph, at least by my standards. So let's head off to the chalkboard and see how we can do this. Let's find these deltas for part A and part B. All right, folks, this example, we're kind of easing ourselves into this epsilon delta concept before we actually do an epsilon delta proof. Keep in mind, I said this is somewhat like a game. I always viewed it as a game. Someone gives an epsilon, you have to find the delta. Epsilon that's how close they want to be to the limit, so that's like the y's, the range values. Delta, you have to find the delta to determine how close they have to be to an x, so delta kind of matches up with the domain. So let's look here at this example. I said there's some function out there, and the limit as x approaches 2 of the function is 6. And that's the graph that I said I would put on the board. I didn't have enough room on the slide to show you the graph, but that's the graph. So please take some time to get that graph in your notes. I told you to leave room for it. We're going to determine delta. Helps if I can spell determine correctly. We're going to determine the delta greater than 0, where if 0 is less than absolute value, x minus 2 is less than delta, then the absolute value of f of x minus 6 is less than 2. So here's the game aspect. This 2, that's an epsilon that someone has given. And that absolute value statement is saying they want all function values minus that limit 6, they want it to be within 2 units of 6. So they're telling a region around that limit of 6. So I come over here and I look at 6. And it's like, okay, they're saying they want to be within 2 units of 6. So I come up 2 units. That puts me here. And then I come down 2 units. That puts me here. So here's what I'm going to do. I'm going to come from a y value of 4, make dashed lines over to the graph of my function, because that's 2 units less than the limit of 6. From the y value of 8, I'm going to make some dashed lines over to the graph of the function. So the person is playing the game and they give the epsilon value of 2, they're really saying, how close do I have to pick x's around this x value of 2 so that all the functional values are in this region? Well, if I just kind of drop those down, I think I have the answer to the question. If you pick any x in the interval 1 to 3, so you pick any x in here, the functional values, or the y's if you will be within 2 units of 6. Now any smaller delta would work as well, but we said let's find delta, the largest delta. So my answer here, delta is 1. So I'm saying pick any x within 1 unit of 2. And all the functional values will be within 2 units of the limit 6. So let's look at part B. Part B says absolute value of x minus 2 less than delta. Then absolute value of f of x minus 6 is less than 1. So it's a game. The person has given us a smaller epsilon. Now they want to be just within 1 unit of 6. So within 1 unit of 6. Well, let me do the same thing. Let me draw some dashed lines, come out to the graph, and let me come down to the x-axis. And you know, it kind of looks to me like that's halfway between 1 and 2, and this looks like it's halfway between 2 and 3. So I pick anything I want in that interval, and I keep saying it looks like it's 1/2. I'm within 1/2 unit of 2, so I'm going to say the delta is 1/2. And you know, that's all there is to this one. So now we're going to head back to the slides, and we're going to talk about, you know, the strategy we're going to use to write a formal epsilon delta proof. Don't get freaked out about the word proof. It's not that bad, folks. So let's head back to the slides. All right, so that example, hopefully we solved that game aspect I was talking about. Hopefully we're seeing, you know, how that delta kind of matches up with the domain. How close do I have to be to whatever value of x, you know, we are approaching? The epsilon, that's what someone gives you. They want to be within epsilon units of L. So hopefully we saw the game aspect and it wasn't too bad. But now it's time to do the real deal, folks. It's time to write an epsilon delta proof. Don't get freaked out by the word proof that's being used here. I'm going to give you my plan of attack on how to do an epsilon delta proof. This is something that I wish I had seen the first time I encountered an epsilon delta proof. No one showed me this, but I'm happy to share it with you. So here's my attack plan. Part 1, we'll write down what our goal is. Then we're going to just play around. We'll play around and we will determine delta by playing around. Then we will write the formal proof. So let's see what I mean by all of this in this example. Let's prove that the limit as x approaches 2 of 2x plus 1 equals 5. I mean, I think we clearly see the limit is 5. Let's prove it. So write this down. Leave plenty of space. I'm going to go off to the chalkboard. You're going to see how I write down the goal and I play around kind of off to the side, and then I will write the formal proof. So here we go to the chalkboard. All right, this example, we are going to prove that the limit as x approaches 2 of 2x plus 1 equals 5. We know it's 5, but now we're going to prove that it's 5. And I told you I would show you how to attack these problems. This was never shown to me. I wish it had been, you know, but when I saw this stuff, the person would just write down proof and then just started to write stuff out, and I had no idea where anything was coming from. We're going to figure out where it's coming from. So we do this off to the side. This isn't part of the proof. This is like off to the side. We write down what our goal is. Now in general, the goal is you want to take the absolute value of x minus a less than delta and show that that implies absolute value of f of x minus L is less than epsilon. For this problem, our goal is absolute value of x minus 2 less than delta implies absolute value of f of x. Well, f of x is 2x plus 1 minus L. L is 5 is less than epsilon. So our goal is we want to show absolute value of x minus 2 less than delta implies absolute value of 2x plus 1 minus 5 is less than epsilon. We've written down the goal. And then what did I say next? The next thing you were going to do is play around until you determine delta. So here's what I mean by play around. It comes from this piece right here. So let me just pull it out and write it down again. All right, I just wrote down the absolute value of 2x plus 1 minus 5 is less than epsilon. Okay, this is the exact same thing, so I'll use a double-sided arrow, that if I just clean up what's inside the absolute values, I mean there, I just got rid of the parentheses. And then that's the exact same thing. If I combine like terms, I would have 2x minus 4. And I'm going to continue playing around inside the absolute values. It looks like I could factor out a 2. And then I can use a property of absolute values. The absolute value of 2 times x minus 2. That's the same thing as the absolute value of 2 times the absolute value of x minus 2. Well, we know what the absolute value of 2 is. The absolute value of 2 is 2. And then I'm just left with absolute value of x minus 2. And then, still playing around, divide both sides of the inequality by 2. And look at where we're at. Just make a comparison. Look at our goal and look at where we're at in our playing around. Absolute value of x minus 2, absolute value of x minus 2, less than, delta, epsilon over 2. Doesn't it look like delta is equal to epsilon over 2? That's the key. Delta is equal to epsilon over 2. We're done with the goal. We're done with the playing around. Now we write the proof. And here's how every proof would start off. Well, first we write down the word proof. No one ever sees this. We do that off to the side, and then we come over here and write the proof. So you write proof, and then you write down, let an epsilon greater than 0 be given. For this problem, we will choose delta to equal epsilon over 2. And see, when I learned this stuff, without ever seeing any of this, I had no idea why the professor was saying, let's choose delta to equal epsilon over 2. I had no idea why. So, choose delta equals epsilon over 2. Then, and this is going to look familiar, then we write down 0 is less than absolute value of x minus 2 is less than delta. Then absolute value of x minus 2 is less than, and here's where we put the epsilon over 2 in for delta. And now we just kind of reverse our steps of playing around. I mean, multiply both sides of this inequality by 2. That's not too bad. Bring this back inside the absolute value. You can distribute the 2 here. And then you could say, well, you know what, this 2x minus 4 is really the result of the quantity 2x plus 1 minus 5 and you're done. You have shown that absolute value of x minus 2 less than delta implies absolute value of f of x minus L is less than epsilon. So like I said, when I learned this stuff, this was just written on the board. I had no idea what was going on. You can figure out where it's going on. You know what is going on. It's coming around from what I just showed you. Do this off to the side or do it on another piece of paper. Just, it's your guidance for actually writing down the proof. And you know what? I'd like you to try one of these right now. So go into the section 2.7 exercises. I would like you to try number 20. It's doing a proof. So pause the video, do number 20, and then restart the video, and I'll be here at the board working through it to make sure you got this epsilon delta proof written down nicely. All right, folks, in number 20, you were asked to prove the limit as x approaches 3 of negative 2x plus 8 equals 2. So that's my general goal statement for this problem. This is the specific goal. A was 3. F of x is negative 2x plus 8. The limit L is 2. So now it's time to play around. So remember, your playing around starts with this step. Negative 2x plus 8 minus 2 less than epsilon. That's in absolute values. This is the exact same thing as if I get rid of parentheses and combine like terms, I have a negative 2x plus 6. That's inside absolute values, less than epsilon. Inside the absolute values, I could factor out a negative 2. I factor out a negative 2. That leaves me with an x minus 3. Then that old property of absolute values, this is the absolute value of negative 2 times the absolute value of x minus 3. Well, what's the absolute value of negative 2? That's right, it's 2 times absolute value of x minus 3. Divide both sides by 2. And it looks like, just comparing this to this, delta is equal to epsilon over 2, which was the same delta we had in our example. Please do not believe that every delta is epsilon over 2. It just happens to be a coincidence. So here we go. Now we write down the proof. So proof. Let epsilon greater than 0 be given. Choose delta to equal epsilon over 2. Then 0 is less than absolute value of x minus 3 is less than delta. Well, that's absolute value of x minus 3 is less than epsilon over 2. That's the same thing as multiply both sides by 2. 2 times absolute value of x minus 3 is less than epsilon. This is the same thing as saying absolute value of negative 2 times x minus 3 is less than epsilon. Remember, absolute value of negative 2 is 2, so we're taking that and putting it back inside the absolute value and calling it a negative 2. And this is the same thing as absolute value of negative 2x plus 6 less than epsilon. And then that negative 2x plus 6, we could rewrite negative 2x plus 6 as the quantity negative 2x plus 8 minus 2 is less than epsilon. And we are done. We have shown absolute value of x minus 3 less than delta. So that's absolute value of x minus 8 less than delta. We have shown that implies the absolute value of f of x minus L is less than epsilon. All right, folks, let's head back to the slides and see what's next. All right, folks, I hope you saw that doing one of these epsilon delta proofs wasn't too bad. Hopefully you were able to do number 20. But let's see what's left in this section. It's just some comments I have for you. You know all those limit laws and limit theorems that we've seen so far in this chapter? All of them can be proven to be true thanks to the formal definition of a limit. We couldn't prove them to be true without this formal definition of a limit. In fact, the two guys that are considered with discovering calculus, Isaac Newton, he was an English dude, and Leibniz, he was a German dude. They kind of discovered it at the same time, independent of each other. They did not have a good definition of a limit. They didn't have a real good definition of a limit. They were operating under the weak, really, really, really close that we saw in section 2.2. It wasn't until a guy named Karl Weierstrass came around and Cauchy, and they were able to quantify what it meant to be really, really close. And then all those limit laws that we saw, boom, we're able to prove them to be true. So as an example of what I'm talking about, feel free to read example 6 on page 100. It's just an example showing the proof of a limit law we've already seen earlier in the chapter. But at the end of the day, every limit law and theorem we've seen so far, I just want you to appreciate they really are true, and they're proven to be true by using the formal definition of a limit. And then there's one more extra homework problem I'd like you to do. Besides the one that are assigned in section 2.7, I'd like you to prove that the limit as x approaches 1 of 5x minus 2 is equal to 3. So folks, at this time, that's it. I don't have a whole lot exercise-wise for you to do in section 2.7, but you have everything that you need to know in order to do the exercises. So go do the exercises in section 2.7, and thanks for watching.